You know, when you go out to eat at a really high-end restaurant, you might order this incredible, just mind-blowing dish.
Oh, yeah, absolutely.
And naturally, you want to know how they made it.
Wow.
You ask the waiter for the recipe, but they just sort of smile and shake their head.
Right, the kitchen doors are locked tight.
Exactly. It is a closely guarded secret. I mean, you get to eat the food, but you have zero idea what actually happened in the back.
Yeah, you are tasting the final product, but the actual process, like the specific ingredients, the prep work, the temperatures, that all remains a total mystery.
And that dynamic, that exact feeling of being locked out of the kitchen is what is happening right now in the very cutting-edge world of artificial intelligence, specifically with something called Agentic AI.
It really is.
Welcome to the deep dive, by the way. Today, we are taking you behind those locked doors. Just to set the stage for you, when we say Agentic AI, we are not talking about those standard chat bots where you type a prompt and get, a poem or a chocolate chip cookie recipe back.
No, not at all. We are talking about AI agents that can actually operate a computer on their own.
Right.
They navigate file systems, they write complex software, run that code, read the error messages when it inevitably breaks, and then they debug their own work.
Which is wild to think about.
It really is. They perform multi-step, complex tasks completely autonomously, essentially acting as digital workers.
And the models driving them, like Claude Code or DeepSeek V4, are incredibly capable. But here's the problem. The big tech companies building them are keeping the training data an absolute secret.
Yeah, and it's become the defining bottleneck in OpenAI research right now.
It's just a total roadblock.
Totally. To give you an idea of how extreme this secrecy is, look at the recent release of DeepSeek V4. The researchers published a massive 50-page paper detailing the model's architecture.
50 pages.
Right, 50 pages of the raw mechanics of their training process. But when it came to the actual training data, the specific information they fed the model to make it so smart, they dedicated exactly 2 paragraphs to it.
I mean, 2 paragraphs out of 50 pages.
It's crazy.
It's like publishing a cookbook that tells you everything about the temperature of the oven, the shape of the whisk, the exact dimensions of the baking pan, but flat out refuses to tell you what ingredients to put in the bowl.
Exactly. And that leaves independent researchers and the open source community completely in the dark.
Right, because without the data.
Yeah, you can have all the computing power in the world, but if you don't know the recipe for the data, you cannot train a broadly capable agent.
Which brings us to the mission of our deep dive today. We are looking at a groundbreaking new preprint paper called Data Recipes for Agentic Models.
It's a fantastic paper.
It really is. It comes from the OpenThoughts-Agent project, which is this massive open science collaboration involving researchers from UC Berkeley, Stanford, and a host of others.
And they basically decided to pry open that black box.
Yes, finally. Based on over 100 controlled experiments, they are sharing the exact secret sauce of AI agent training. We'll show you exactly what makes a competent AI agent tick.
So to crack open that black box, the research team focused heavily on the foundational phase of training, which is called supervised fine-tuning, or SFT.
Okay, let's unpack this for a second, because SFT is a term that gets thrown around a lot.
It does, yeah.
If we think about training an AI from scratch, SFT is essentially the textbook and the homework phase, right? You are giving the AI explicit examples of problems paired with the step-by-step correct answers.
Exactly. You are saying, here is a mess, and here is exactly how a professional cleans it up.
Right.
But the open question was, what exactly should be in that textbook? If you want an AI to be a great general-purpose agent, what flavor of homework actually builds competence?
So how do they figure that out?
Well, the OpenThoughts team tested 95 different task generation strategies, 95 completely different sources of homework.
I imagine going through 95 different strategies takes an enormous amount of trial and error. What actually rose to the top?
The best results came from a very specific mix. It was a combination of synthetic computer-generated issue resolution tasks datasets like SWE Smith, which simulate complex software bugs mixed with human-written infrastructure questions.
Oh, like real human problems.
Yeah, right. Think of the highly technical, frustrating questions real people ask on forums like Stack Exchange Superuser.
I know those forms well.
We all do. And when they blended the synthetic bug fixing with real human IT problems, performance spiked across the board.
So having a good mix of problems is step one. But setting up the questions is only half the battle, right? You also need the answer key.
You do.
You need a teacher model to actually generate the step-by-step solutions that the new untrained AI is going to study. Now, logically, if I want to generate the absolute best training data, I should just take the absolute smartest, most state-of-the-art, billion-dollar AI model available and have it write all the answer keys.
That would be the assumption.
Why would I use anything else?
It seems completely intuitive. You want the smartest tutor for your student. But what's fascinating here is that the researchers found the exact opposite.
Wait, really?
Yeah, the strongest model on paper does not necessarily make the best teacher in practice.
Wait, you're telling me the smartest AI is a bad teacher?
Actually, yes. In their ablation studies, where they, systematically swap out one variable at a time to isolate the effect, they tested a model called GPT 5.3 Codex.
Correct.
On the raw benchmarks, GPT 5.3 Codex was the absolute strongest model available. It was the reigning champion for getting the right answer.
So it should be the best teacher.
You'd think. But when they used its outputs to generate the training trajectories for the new AI to learn from, it was a surprisingly poor teacher. The student model just didn't improve as much as they expected.
Oh, wow. Then who was the better teacher? What model did they actually use to write the answer keys?
They used an older, slightly less capable model called GLM 4.7 AWQ.
Really? An older model?
Yep. And remarkably, using that older model's outputs as the training data actually resulted in a 5% performance increase for the new agent on their major terminal benchmark.
That is wild.
Okay.
But if you think about it, it actually makes perfect sense when you relate it to human dynamics. Think about the workplace, or even back in high school math class.
Oh, definitely.
We have all met that brilliant savant, the person who just intuitively understands complex calculus or coding architecture.
Yeah.
But they often make terrible mentors.
Because they skip all the foundational steps. They don't expose the connective tissue of their thought process.
Exactly. You ask the savant how they solved a server crash, and they just say, well, obviously it's just a misconfigured port. And you're left staring at a blank screen, completely lost.
Yeah, they leap straight from problem to conclusion.
But the person who maybe had to struggle a bit, who methodically works through the problem step by step, writing at their thought process, checking their work, that person makes the perfect teacher because they actually show the mechanics of the solution.
The data strongly backs up your analogy. A slightly less powerful model produces exhaustive, methodical reasoning steps. It explains its work.
And that's what the student AI needs.
Precisely. That provides far better supervision for a learning AI than a supermodel that just spits out the right answer as if it were magic.
Okay, so if I've got this patient, methodical teacher generating my homework, does it matter how long the homework assignments are?
What do you mean?
Well, I'm assuming a quick multiple-choice question doesn't hold the same weight as a long multi-step essay.
Ah, right. It matters immensely. Which brings us to the concept of rollouts or execution traces.
Execution traces.
Yeah. An execution trace is the recorded transcript of all the steps the AI takes to solve a problem. It tries a command, reads an error, thinks about it, and tries another command. Each one of those back and forth interactions is considered a turn.
Got it. And when they were looking at all these thousands of generated homework examples, they had to decide which ones to keep in the final textbook and which to throw away.
Yes.
What was the filter?
They discovered that filtering out the short execution traces drastically improved the quality of the dataset. Specifically, they decided to throw out any trace that was resolved in fewer than 5 turns.
5 turns.
Right. They only kept the traces where the AI had to engage in 5 or more back and forth interactions with the computer environment to finally nail down the solution.
I have to play devil's advocate here, though.
Okay, go for it.
If you are only keeping traces with 5 or more turns, those traces are naturally going to be much longer text files.
Yes, they are.
They contain way more words, or in AI terms, way more tokens. So is the AI actually getting smarter because of the friction of multi-turn problem solving? Or is it just getting smarter because you are brute forcing it with more total data and more compute time?
That is a brilliant pushback, and it's exactly the critique a machine learning engineer would level at this paper. Is it the quality of the struggle or just the raw volume of words?
Right.
To answer this, the researchers ran a strictly compute-controlled ablation. They leveled the playing field entirely.
Meaning they gave 2 models the exact same data budget.
Precisely. They set an equal token budget for 2 different training runs. In one, the model was trained on a random sample of traces, including short ones.
Okay.
In the other, it was trained only on the 5-turn minimum traces, but they cut the total number of examples off, so the raw amount of training compute was absolutely identical to the first run.
Oh, so they completely neutralized the volume argument. Did the longer debates still win?
The five-turn filter won by over 5 percentage points on the rigorous SW bench evaluation.
Wow. So it has nothing to do with raw volume. It's like the difference between sitting in your room memorizing a stack of flashcards, which is quick single-turn learning, versus engaging in a deep, hours-long debate with a professor.
That's a great way to put it.
Even if the flashcards contain the exact same total number of words as the debate transcript, the debate teaches you something fundamentally different. It teaches you how to reason, how to handle frustration, and how to pivot your logic when your first argument falls flat.
Exactly. By forcing the AI to train on those multi-turn traces, they were teaching it the skill of perseverance. Think about what happens in a five-turn trace.
Right, it's failing a few times first.
Yeah, the AI tries a command, it fails, and the terminal spits back an ugly error message. The AI has to read that error, understand why its initial assumption was wrong, and generate a new plan.
It's actual problem solving.
It learns state management and error recovery rather than just memorizing a straight line to the finish.
Okay, so we have the perfect methodical teacher, and we have the five-turn filter to ensure the AI learns perseverance. But to build a world-class AI, quality alone won't cut it. You need scale.
You definitely need scale.
The team set a goal to build a massive data set of 100,000 high-quality examples. But when they tried to scale up, they hit a massive brick wall.
Yeah, they hit what is known in the field as the scaling wall. Initially, they took their top 4 task sources, those high-quality coding and infrastructure problems we just discussed, and they just generated more traces for them. But as they pushed the data set from roughly 31,600 examples up to 100,000, the model's performance completely flatlined.
So more data entirely stopped equaling more intelligence.
Exactly.
Once they hit that wall, their only logical move would be to add in new sources of data, right? Like expand the pool.
That is exactly what they tried. They expanded from their top 4 sources to the top 16 sources. They threw everything at the wall to hit that 100,000 number.
Did it work?
No. Doing that actually hurt performance on every single benchmark.
Wait, why would more data make the AI dumber?
Think about dumping a cup of salt into a perfectly balanced soup just because you wanted more volume in the pot.
Oh, it ruins the dish.
It dilutes the underlying patterns.
Yeah.
The lower quality sources introduced contradictory formatting, simpler problem structures, and noise. It confused the model, dragging the whole system's performance down.
So they are completely stuck. They can't just repeat the top 4 sources because the AI stops learning new things.
Right.
And they can't add new sources from further down the list because the lower quality poisons the well. How do they break through?
The breakthrough came from a technique called synthetic task augmentation. Let me give you a specific example from the paper that illustrates this perfectly.
Okay, I'd love to hear it.
One of their absolute best top-tier sources was a data set from Stack Exchange about the cryptocurrency Tezos.
Tezos, that is a highly technical, very niche topic.
Very niche. In fact, that specific data set only contained 997 unique problems.
That is a tiny drop in the bucket when you're trying to reach a 100,000 example data set.
Exactly.
So if you can't scrape the internet for more Tezos problems because they just don't exist, what do?
Well, instead of hunting for brand new problems, they used an LLM to synthetically rewrite and expand those existing 997 core problems into over 21,000 distinct variations.
So what does this all mean for the actual data? They basically took a core question like, how do I configure this specific crypto wallet?
Yes.
And they had the AI rewrite the prompt to be, I'm getting an error code on my digital ledger, how do I resolve it? Or what are the terminal commands to initialize this blockchain tool on a Linux machine?
Exactly. The core underlying technical mechanism required to solve the problem remained exactly the same. But the surface-level presentation, the phrasing, the imaginary user's tone, and the context were entirely different.
Well, that's clever.
And when they trained the agent on these augmented tasks, the performance flatline disappeared. The metrics started climbing again, breaking right through that scaling wall.
That is such a vital insight for you listening, whether you're building software or just trying to understand how these tools work. Instead of asking the AI 10,000 superficial, entirely different questions, they asked it 1,000 core questions, 10 different ways.
It's all about how you frame it.
Yeah, it proved that the true bottleneck to scaling AI intelligence isn't the raw volume of distinct facts. It is the diversity of how tasks are described. It forces the AI to recognize the underlying architecture of a problem, regardless of how chaotic or poorly worded the user's prompt is.
This was the final crucial piece of their supervised fine-tuning recipe. They secured the methodical teacher, they enforced the multi-turn friction filter, and they cracked the scaling wall with synthetically augmented task diversity.
And so we arrive at the grand culmination. They take all these incredibly specific, hard-won data curation choices, and they put them into the oven.
Yes, the final bake.
You take a base model, specifically the Qwen 332B model, which is an open weights foundation, and they fine-tune it on this meticulously crafted 100,000 example dataset. And before we get to the score, I just want to highlight why this synergy is so powerful.
Please do.
You are taking a solid foundation, feeding it methodical stepping stones so it sees the math, forcing it to struggle for 5 turns so it builds resilience, and then presenting those struggles in thousands of different disguises so it doesn't just memorize syntax.
It creates an incredibly robust digital mind. And the result of that training run is a brand new model they call OpenThoughts-Agent 32B.
The moment of truth. How did this open source recipe actually stack up against the competition?
It was a massive victory. Across 7 highly rigorous agentic benchmarks tests that measure real-world software engineering, terminal use, complex tool calling OpenThoughts-Agent achieved an average accuracy of 34.8%.
Now, I know 44% sounds like a failing grade if you're thinking about a middle school history test.
Right, in a traditional sense.
But in the bleeding edge world of autonomous AI agents navigating real computer systems, 44% is staggering.
It's massive. To put it in proper context, it beat out the strongest existing open data model in its exact size class, a model called Nemotron Terminal 32B, which scored 40.9%.
Oh, wow. So it wasn't even that close.
No, OpenThoughts-Agent utterly dominated on the most critical, real-world coding benchmarks, specifically SWE Bench Verified and Terminal Bench 2.0. The open recipe absolutely worked.
It is an incredible achievement. But SFT, this textbook phase of learning we've been deep diving into, is really just the first act of modern AI training.
Yeah, it's just the beginning.
SFT is phenomenal for teaching the AI the rules of the road, but to create a truly autonomous, resilient agent that can handle the wild west of the internet, you eventually have to take the training wheels off.
And that brings us to the second phase, reinforcement learning, or RL. Because of the sheer computing power required for RL, the researchers scaled down to test these specific mechanics on an 8 billion parameter model.
Let's make sure we ground this concept too. SFT is mimicking a teacher who has already provided the answer key.
Correct.
RL is where you teach the AI through trial, error, and reward with no teacher in sight. It's not about following a script anymore. It's like putting the AI in an escape room.
That's a good analogy.
It can try 100 different combinations on the padlock, but the door only opens, and it only gets the reward if it eventually figures out the exact right code on its own.
And just like with the SFT textbooks, they wanted to know, does the flavor of the RL escape room matter?
Did they test a bunch of them again?
They did. They tested various environments to see what produced the smartest agent. The surprising winner was a dataset called PyMethods-2 test.
PyMethods-2 test? That sounds incredibly dry.
It is a bit dry, yeah.
What exactly is the AI doing in that environment?
It is a dataset of highly complex competitive programming puzzles that have been transformed into strict Python contracts.
What do you mean by a Python contract?
In software engineering, a contract means the code has to behave in an absolutely predictable way. You feed it a specific input, and it must produce a mathematically exact output to pass a suite of invisible tests.
Oh, okay.
There is no room for interpretation. It is highly constrained, deeply logical, and the reward is entirely binary.
So there is absolutely no partial credit. You can't write a poem that's close enough. You either pass the invisible test or you fail and get nothing.
Exactly. And what's fascinating is how this strict environment altered the AI's internal mechanics.
How so?
It didn't just teach the AI how to write better Python syntax, it fundamentally altered the AI's emergent behavior. It forced the AI into a state the researchers called legitimate exploration.
Legitimate exploration. What does that actually look like in the raw data?
The metrics shift dramatically. After training on this strict competitive programming dataset, the number of think tokens, which is the internal reasoning the AI generates before it takes an action on the computer, spiked by 116%.
Wait, it more than doubled the amount of time it spent thinking before acting?
Yes. And the phrases indicating self-correction things, where the AI essentially says to itself, wait, that logic doesn't hold up, let me back up and try a different approach, those phrases shot up by 81%.
That's amazing.
The RL environment taught the AI to become a patient, highly thorough explorer. It learned through trial and error that if it didn't think deeply and aggressively test its own assumptions, it would never crack the Python contract and get the reward.
Here's where it gets really interesting, though,
Mhm.
because the researchers contrasted that patient explorer behavior
Mhm.
with what happened when they trained the exact same base model on a totally different RL dataset.
Yes, they use a dataset called LM Verifier Freelancer.
Okay.
Unlike the strict Python contracts, this dataset focused on broader, much more open-ended tool use tasks. It was less like a strict escape room and more like a creative writing assignment, where you might get a passing grade just for showing up and turning something in.
And training on that open-ended dataset did the exact opposite to the AI. It taught the AI to drastically compact its behavior.
It really did.
Its thinking tokens plummeted by 42%. Its self-correction dropped by almost 60%. It turned the AI from a patient genius into a rushing amateur.
Yeah, it learned to just blast through the task, taking wild shortcuts.
Right, and often just abandoning complex problems entirely because the environment didn't strictly penalize it for doing so.
It proves that the specific flavor of the practice test completely rewires the AI's operational personality.
Personality, yeah.
One environment breeds patience, rigor, and deep thought, while the other breeds impatience, corner cutting, and shallow execution.
It is just mind-blowing that the structure of a digital puzzle can induce what basically looks like a personality shift in a neural network.
It's fascinating.
So let's bring this all together. We started this deep dive staring at a locked kitchen door, the secretive black box of big tech AI training, where we only got 2 paragraphs explaining how the magic happens.
Right.
But thanks to the open science rigor of the OpenThoughts-Agent project, we've walked out with a fully transparent, heavily tested recipe.
We learned that the smartest AI in the room doesn't necessarily make the best teacher. You need a model that explicitly shows its work and exposes its reasoning. We saw that filtering data to force an AI to endure multi-turn, 5-step struggles actually builds the vital skills of state management and error recovery.
We saw how asking the exact same core question in a dozen different ways breaks through the scaling wall by teaching the AI diversity over raw volume.
Exactly.
And finally, we saw that the specific strictness of reinforcement learning puzzles entirely dictates whether your AI acts like a methodical, self-correcting explorer or someone just trying to clock out early on a Friday.
Which is such a powerful takeaway.
It really is. And for you listening, there's a very human application to all of this. If you were trying to master a new skill in your own life, whether it's coding or cooking or, a new language, don't just seek out the brilliant savants.
Seek out the mentors who actually take the time to explain the steps.
Yes. Don't shy away from the friction of multi-step struggles. Embrace them, because that is where the real resilience is built.
Yeah.
And remember to vary your practice to build robust, flexible understanding.
The parallels between how we optimize machine learning and how we optimize human learning are genuinely remarkable. It all comes down to the quality of the struggle.
It really does. And it leaves us with one final, lingering thought for you to mull over as you go about your week. If just slightly tweaking a training data set, changing a Python contract to an open-ended task can completely alter whether an AI acts like a patient, thorough explorer, or a lazy, corner-cutting rusher.
Yeah,
What does that mean for the AI assistants you interact with every single day?
that's the real question.
The next time your AI gives you a hallucinated, rushed, or just plain lazy answer to an important question, ask yourself, is that actually a technical bug in the code? Or is it just a perfect reflection of the rushed, corner-cutting homework assignments it was fed behind those locked doors in a lab?